Okay, I think we're live. Can you guys hear me and can you see my screen? Just type yes or no. Okay. And the is the font readable? So I think last time some of you complained that it wasn't readable in 4K. Okay. Um, so I'm doing streaming in 1080p now, but it might be a little bit blurry because I'm doing this dynamic scaling, or at least it's a bit blurry on my screen. Um, that's alright. That's fine. You don't need to see me. You just like listening to my voice, do you? Okay. So sorry I didn't post the topic yesterday, but what I wanted to talk about today is the kernel cache aliasing or merging, specific to the SLUB allocator, the SLUB or the unqueued allocator on both Android and Linux systems, and the way it merges general purpose and special purpose caches. And as you probably know from the exploitation point of view, this is very useful. If you've got, for example, let's say a use after free and your vulnerable object doesn't have any function pointers or data pointers, or any other useful data that you can override to get control over the RAP pointer, or instruction pointer, or escalate your privileges somehow, but that object is allocated in one of the general purpose caches, then you're lucky and you've got more chances to exploit it successfully than if, for example, your object is in some standalone special purpose cache and it's not getting merged with anything else on the system. So that's what I wanted to talk about, this aliasing process. Specifically, aliasing for special purpose caches, how they get merged with general purpose caches or other special purpose caches on the system. And we've had actually a few cases where the same bug, for example, use after free was exploitable on x86 64, but it wasn't exploitable on Android on ARM64. Even though it's the same allocator, it's the same bug, exactly the same execution path, but the difference is really the layout of those general purpose caches on the Android system. Right, the smallest cache on Android is kmalloc 128, but I'll talk about this shortly. So anyway, I'll probably start with the general purpose allocations, just for completeness. So if I do something like this, the kmalloc, and let's say I'm trying to allocate 220 bytes, and it's a standard GFP kernel allocation. Right. So if I allocate my object with kmalloc, which general purpose cache is it going to be allocated in? So let's list my proc slab info. Right, so these are all my general purpose caches, my kmallocs. So which cache is it going to be allocated in? Yep, 256. Yeah, it's not exactly because it's a power of two, but yeah. So what I typically hear is that you take the object size and you round it up to the next power of two, and then you find your general purpose cache. As you can see, there are, like, most of them are power of two. So 8, 16, 32, 64, but there are some exceptions. So there is kmalloc 96, and there is kmalloc 192. Right, so the rule is actually you take the next smallest cache available in your system that can fit your object. Right, so it doesn't have to be power of 2. Right, so in my case, yeah, this is 220 bytes, and the next smallest cache on my system that can fit my object is kmalloc 256. Right. So this is pretty straightforward with the general purpose caches, right? And as I said, if you get your if your vulnerable object is in a general purpose cache, then you're lucky. But sometimes, and I'd say most of the time, your vulnerable object would be in a special purpose cache. So the API for special purpose allocations is something like this. So first you do kmem-cache create to create a cache, and the first argument is the name of your cache. So you can call it whatever you like. In my case, it's my cache. And let's do the what we did before, 220 bytes. So this is the size of the object in that cache. Then 0 is the alignment, so typically you'd see 0 here. And then the flags for the cache. And you would normally see at least SLUB hardware cache align, meaning that the cache needs to be aligned on the cache line size. So aligned on 64 bytes. And on both x86-64 and Arch-64, the cache line size is 64 bytes by default. And it makes sense, right, for performance reasons that you would use at least hardware cache align when you create your caches. And once you've got the cache, you can start getting allocations from that cache with kmem cache alloc. So pointer to the cache that you've just created, and let's say again it's a standard kernel allocation. Right, so if now let's do void pointer. So if I would compile and load this module now, is my cache, my special purpose cache, is it going to be aliased with any other general purpose caches, with any of the kmallocs here? Yep, 256, but why 256? Forget about that power of 2. It's has nothing to do with the power of 2. I mean, yeah, if I take this object 220 bytes and I round it up to the next power of 2, it's 256, but it has nothing to do with that. So it actually gets aligned on the cache line size, right, on 64 bytes. And if you align it on 64 bytes, you get 256. So it gets merged with the kmalloc 256 cache, right? And this is what I really wanted to talk about, this aliasing process, aligning on specifically on the cache line size. Yeah, let's compile it and load it. So sudo test module. And let's check the aliasing information. Kernel SLUB. So grab my cache. Right, so it gets aliased with this cache here, and then so you can see that my cache is now aliased with the kmalloc 256 cache, the general purpose cache. What, the syskernel SLUB? This just shows you all the aliasing information, right? So all the symlinks that you see here are the aliases. So basically, it's saying that this, for example, the task group special purpose cache gets aliased with this, right? and then you can, based on the symlinks, you can find aliases. So in my example that I showed you here, that means that all these special purpose caches, this bio, biovic, keyjar, etc., and the general purpose cache kmalloc 256, they all get alias together. So essentially it's one cache. It's the same cache. Yeah. So there is another tool called slubinfo.c that comes with your kernel source code. So a C file that you compile, and I think the flag is -a to show the aliasing information, and it would show you exactly the same information, but in a more sort of readable, in a nicer format. But essentially that's what it does, that tool. It just passes this directory structure and it prints it out in this nice format. But you can just do it manually. Yep. So this aliasing, the aligning on the cache line size. I just wanted to show you the implementation of that. So I think it's an SLUB C. So cache alias, kmem cache alias. This is the function that gets called when you create your new cache. And the first function that it calls is find mergeable. So that function tries to find a cache that can be aliased with your new cache that you're trying to create, and it returns the pointer to that cache s. So if it found a cache that can be merged with, if it's not null, then you increment the reference counter, and then essentially you would call sysfs slab alias. So this function just creates that alias, so the symlink in the sysfs directory here, and then it just returns that cache. So let's take a look at find mergeable. And find mergeable is in slab common. Okay, so this is the implementation of the function. So first checks this global variable slab no merge if it's set, and this variable actually gets set if you've got, for example, kernel address sanitizer enabled. Then this variable gets set, and then all caches on your system become standalone caches, so they don't get merged at all. Just to make it easier to pinpoint the vulnerable cache when you trigger a bug. Right, and then it gets to here and it starts computing this alignment. We'll get to this function calculate alignment shortly. Then checks a few flags. Right, you can actually set this flag slab never merge when you create your cache, and then it becomes a standalone cache. And then there's this for loop. So for every cache on your system, it just tries to find the cache to merge with. So it checks the size, and if it finds the right size, then it returns that cache, right? And it merges your current cache with that cache. So let's take a look at the calculate alignment. Right, so remember that flag that we had earlier. So slab hardware cache align, so aligning on the cache line size. So that's what we're doing here. So first, our align is the cache line size. By default, this would be, as I said, 64 bytes on x86 64 and on ARM 64. And then if the size of the object is less than the cache line size divided by 2, then you set align to a half of that value, and you just keep doing this in a loop. So you're trying to find the smallest value that fits your object, basically. So in our case, in our example, the object size was 220 bytes. So it's obviously greater than the cache line size. So we just skip that, and then we get to this. So align, and this align here is what this is the user provided align. Remember that 0 for the alignment when we created the cache. So this is 0 or align, right? 64 bytes. So our align variable becomes 64 bytes. So we check if it's less than the minimal architecture's value. If it's not, then you just align the object on that cache line size. So in our case, 220 bytes gets aligned on 64 bytes on the cache line size, and that becomes 256 bytes, right? And because there is this cache, there's this general purpose cache kmalloc 256 on the system, that for loop that I showed you earlier would find that cache, would find the right size, saying okay 256, and it'll get merged with that cache, the general purpose cache kmalloc 256. What if we what if the object was say 16 bytes or something like that? So let's go back to the module. So let's say instead of this 220 we do 16. So what's going to happen there is there's hardware alignment on that cache. Is size less than the 64 divided by 2? Is it less than or equals to 32? It is. So you set the R-line value to 32 and you go for another iteration of that loop. So is 16 less than 32 divided by 2? Less than or equals to 16? It is. So you do this again, right? And then you get to here. Your R aligned value is now 16, right? This is the smallest value that fits your object. And your align value, this is a user provided variable 0. So max of 0 and 16, the alignment becomes 16. So essentially your object is now aligned on, gets aligned on the 16 bytes. Right, so let's try this. Let's name it my cache 16, and then just recompile this. So reload the module. What did I call it? Test mod. So, and then reload it. And then let's check the aliasing again. Right, so you can see that my cache is now aliased with this cache. And this is the general purpose kmalloc 16 cache. Right. So this is really nice from the exploitation point of view, right? Depending on the object size, it's likely that your special purpose allocation will get aliased with one of the general purpose allocations, and that's on x86-64, right? As I said, on Android it's a little bit different. So let me just connect my test device. So I'm just connecting my Galaxy S9. Okay, so SLUB info. As you can see on Android, the smallest general purpose cache is kmalloc 128. Then we've got 256, 512. They just double up to 2 pages. Right, so the layout is a little bit different, and this is good and bad on Android. So the downside is obviously we've got less general purpose caches. Right, so if we've got the same example that we had before, the kmalloc 16, so the special purpose allocation, 16-byte allocation, this will not work on Android. So this will not get merged with any general purpose caches because there is no kmalloc 16 cache. Right, so this will become a standalone allocation, or it might get merged with one of the other special purpose caches that are 16 bytes in size. The upside to this, to Android, is, again, since you've got less general purpose caches on the system, and if it just happens that your vulnerable object is in one of the general purpose caches, then you've got more candidates for those for your, say, refill for the objects. So again, let's say my vulnerable object is 16 bytes and it's a general purpose allocation, so kmalloc 16 bytes. If that's the case, on x86-64, this will be in kmalloc 16 cache, right? And I would have a limited set of my candidates for my refill. So all the candidates that are greater than 8 bytes and less than or equals to 16 bytes. On Android, on ARM64, I've got all the candidates up to 128 bytes. So as long as the object gets allocated in a general purpose cache and its size is less than or equals to 128 bytes, that's a potential candidate for my refill. Right, so that's the upside. And that's why I said earlier that sometimes you find bugs that are exportable on x86-64, but it's not exportable on Android, on ARM64, even though it's exactly the same bug and it's the same use after free. And you really have to check if your object is getting merged with or aliased with one of the general purpose caches or any other caches on the system. And it might be that, you know, if you change if the object size gets changed, right, from say one kernel version to the other, and it might not be exportable on the first version that you've checked, but it might get eventually exportable on another kernel version if the object gets aligned on that, cache line size, and it ends up in one of the general purpose caches. So it can happen, but yeah, unlikely though. Yeah. So as long as the caches, as long as you have that general purpose cache of that size, then it will get merged. Right. So in our example on x86-64, we had that kmalloc 16 cache. Right. If we didn't have that, it wouldn't get merged. Right. So same thing on Android. There is no kmalloc 16, so that object becomes that cache, the special cache becomes a standalone cache. Yeah, if it's a special, if it's a general purpose allocation, then yeah. So if you've got a vulnerable object and it gets allocated via kmalloc, kzalloc, the general purpose allocation, then you've got more candidates on Android, right? Because you've got less general purpose caches. Yep. Yeah. Okay. Any other questions? Okay. Awesome. The cred structure. Yeah. Okay. Let me just before we finish up, let me just show you the CRED structure. So my kernel version here is 4.19. So this would be different on 4.4. So kernel CRED. So CRED jar is the cache, the special purpose cache. So let's see where it gets allocated. Okay, so this is where we create the cache, the CRED jar cache. So size of the object. Again, the alignment is 0, and then we've got alignment on the cache line size, panic, and SLUB account. So, okay, this makes it a little bit different, and this is what I was saying. The difference between 4.4 and say 4.19 is this flag here. So SLUB account. If I remove it, then it would be exactly as upstream 4.4. Linux x86-64 upstream 4.4. And this SLUB accounting, it actually makes a big difference. Right, so when you've got this flag SLUB account, your cache becomes a standalone cache. Right, so it's not getting merged with any other caches on the system. Right, and you can have that flag here when you create the cache, or you can have it per allocation. Right, so when you do kmem cache alloc, you can provide this SLUB account flag, and then it becomes a standalone allocation. Right, but let's assume that you've got no SLUB accounting. Right, so let's assume this is a 4.4 kernel, right? The upstream 4.4 kernel. If that's the case, then so let's check the object size. So size of struct CRED. So 168 bytes. Right. So 168 bytes. If we would round it up, so align it on the cache line size, what general purpose cache are we aliasing with? Math. Right. On x86-64. Right, if you recall, we've got kmalloc 192. Right, so if this was a x86-64 system, the say 4.4 kernel up to 4.4, this will get aliased with kmalloc 192, and that's really nice. Again, from the exploitation point of view. But on Android, there is no kmalloc 192. So the CRED jar cache actually a standalone cache. Right, so it's not getting merged with any other cache on the system. Okay, any other questions? Okay, excellent. Thanks guys for joining. See ya.